Right. So if you were to do that young modulus stretching wire experiment, and let's say you stretch something like steel, something that's fairly malleable, normally metal, you will get a graph that looks like the one behind me. Okay. This can be force extension graph, but what I have here is a stress against strain graph. So we'll just make a note here for all of us that they will both have the same shape. All right, so do you need to sketch out the graph? Not really. You should just need to be able to interpret the graph and then also get important information from that graph itself. So you will notice that there are two types, there are two main sections of the graph. Let's say, for example, I start applying force. So when I start applying force, because stress here is force per unit area, okay, this part here is when I start applying some force, and then there is some extension. Okay, so you can see this strain here as extension per unit original length. So as I apply force, okay, this object will have extension. And then you may be thinking, teacher, this one is like Hooke's law. Correct, it is like Hooke's law. Okay, but we are going to continue applying more force until we reach point A. Okay, so we'll apply more and more force until point A. Point A, from O to A, is still a straight line, right? So we will define A as a limit of proportionality, okay? Because OA is a straight line through origin. So what that point means is for all values of F or stress from O to A, F is proportional to X. So for all values of F or stress from O to A, F is still proportional to extension. Okay. And then what about the elastic limit? Okay, because most of the time you are thinking about elastic limit. Well, A and B are actually very close. In this drawing, it happens to be exaggerated, and you can actually say that this part is still kind of a straight line. Kind of, but not really. The A to B portion. Okay. But what is elastic behavior? When we say something is elastic, it means when we let go or remove the force, your object can return to its original length. So elastic behavior would be from O to B. Okay, so elastic behavior is here to here. Okay, we'll define elastic as the ability of the material to return to its original length once force is removed. Once force is removed or stress is removed. Are you very stressed out? If we remove the stress, will you be normal again? That's great. Are you very stressed out? After we remove the stress, you are slightly traumatized and never the same again? Well, that means we have applied too much stress on you. Because if we continue this trend or this graph, okay, and we move on to this part, here is where we have this thing called plastic behavior. Okay, and you may be thinking, teacher, what means plastic, like Barbie doll? Plastic behavior is another way of saying that the object can't return to original length. That's all. Can return to original length, elastic. Cannot return to original dimensions, plastic. So we use length because, like I mentioned just now, in this chapter, we are all doing one dimension. But actually, it is original dimension because sometimes, especially if you do more, it can be in 2D, can be 3D. Okay, original length, original dimensions. So this plastic here, it means the material unable to return to original dimensions. Okay, so any point after that. All right. So another thing, so we will talk about limit of proportionality here by just elastic limit by just defining this as after this, after B, okay, the material, or rather, for all values of F or strain from O to B, material returns to original length or original dimensions when force is removed. Right. Okay, so a few other things that are not that popular that is in this graph would be, you will notice that for the yellow part, you need to apply a lot of force, and then your change in length is very small. This is common for metal. Most of the time, if we have a piece of metal and we stretch it with our hands, you don't expect it to change in length that much, okay? But once you pass a certain point, okay, you will notice that I just need to increase the force a bit, this part here, but then the extension is like very long, okay? This is where necking and hardening will happen. And what necking means is, let's say this is your original, original metal bar, and you apply so much force that the middle part here begin to cave in a bit, something like this. So this is what we call necking. And when necking happens, basically it's just about to break lah. So you can see then here, from here onwards, the force actually decreases because the object is just about to break. And E is when fracture happens. So these are all upper yield stress point, lower yield stress point. This is just extra stuff. Okay. So this D is actually the maximum force or maximum stress that you can withstand. And once you hit maximum, after that, it's very quickly to fracture. All right. So a few things more about the graph beyond just the definition. When you are given a graph, we want to talk about properties such as gradient and also area under the graph, beyond just reading the values of x and y. Okay, so I'm going to build a table to compare the fx and the stress strain graph. Okay, so there are two versions of graph. If you want to find the gradient of your fx graph, recall the Hooke's law equation. F is equal to kx. So if you have an fx graph, okay, your gradient, I'm just going to call gradient g, okay? In this case, g is equal to constant, the spring constant k. All right, so k has many names. You can call it Hooke constant, springs constant, or elastic constant. I'm just going to keep it to spring constant. Okay, but sometimes, just for fun, they will flip the axis, x against f. In this case, your gradient g is equal to 1 over k. All right, because you bring this one over, it's 1 over k. Okay, so whenever you flip the axis, if you are a bit confused, can I write the equation for you? F is equal to kx, right? Okay, so from here, x is your y-axis. This will be equal to 1 over k. So what we are doing is we're actually comparing with the general equation of a straight line. Okay, your y-axis is x, your x-axis is f. Gradient is 1 over k. All right, so learn to move like that. If not, very stressed there. I change the graph a bit, then GG. Okay, one last thing about graph is they don't always give you extension. Sometimes they will give you original length. So please try out questions like that. Don't worry, the gradient is still 1 over k. You just need to shift the graph up or down a bit. Okay, be careful lah, read the graph. Okay, but for the stress strain graph, okay, the gradient, can you think about this? Young modulus, we need equation, right? So Young's modulus, Y-O-U-N-G, I'm going to use E, okay, is equal to stress over strain. So if I have a stress strain graph, let me rearrange the equation again. Stress is equal to Young modulus times strain. Then if you draw a stress strain graph, okay, your gradient will be equal to Young modulus. I highly recommend you to learn to analyze and linearize the graph. Okay, because if you don't, then I will change the equation a bit, then GG. Very important skill. Go and watch the booster videos to do that if you still don't know how to do simple linearizing equation like this. All right. Okay, so this is stress and strain, okay, gradient. If they decide to flip it, then it's 1 over Young modulus law. All right. Okay, so right now, what we have is the idea of the important section of the graph, but I want to talk to you a bit about energy, okay, which kind of comes into play with the second property of that graph. How do we find energy from an fx graph? If you think about your previous chapter of energy and work done, you can find energy of fx by area under the graph. So let's talk about the energy, or specifically the elastic potential energy. Sometimes we call this strain energy. Okay, I'm just going to give it the alternative name, elastic potential energy. Maybe I'll call this EP for this particular recording. Okay, so elastic potential energy, EP, can generally be calculated by half Fx, or it's actually area under the stress strain graph. So because it's area under the stress strain graph, right? Sorry, not area under the stress strain. I'm stressed, so this is also wrong. Area under the force extension graph. Okay, so when we say under, right, I mean it has to be, if you want to use half Fx, it has to be before the limit of proportionality. So before limit of proportionality. Because after that, you can see it's like a curvy thing. So it is still area under the graph, but it's no longer half Fx. Okay. Like for this one, if you want to look for this area, it is half Fx. Half Fx. But if let's say you stretch it to this point here, I don't know, maybe this point, this area is no longer half Fx. Okay. So this, generally speaking, this area is equal to elastic PE, or strain energy. But if they decided to flip the axis this way, please understand it's between the graph and the x-axis. So in this case, your red color point is actually probably somewhere here. Okay, so this is the area, or rather this is the energy stored. Okay, this area is the elastic PE, or strain energy. Okay, so it's not always half Fx. If it exceeds, or if the graph is not a straight line, or if it doesn't obey Hooke's law, then area under the graph. Okay. Second thing, I want to mention roughly that when you look at graphs like this, a pretty important thing is to notice that sometimes there will be an arrow. Okay. What I mean by that is they will draw an arrow here to show stretching. So I'm going to replicate the graph first. Okay, something like this. And then this is called stretch, or stress, stressing the material. Okay, so when you stretch the material, if let's say you stretch until this point, and then when you release the force, it will go back. Okay, this one is stress. And then this is when the force is removed. So I guess I'll write here. Red color, force applied. Blue color, force removed. So all the elastic potential energy is recovered because you return to original length. Return to original length. All elastic potential energy recovered. But sometimes you stretch a bit more, right? You know, so let's say, for example, maybe you went too far this time. You stretch until here. Okay, and then when you return to original, when you remove the force, here is where it removes. So for example, you stretch until this point. Okay, so in this case, if this is your force applied and you return back on this one, your material actually cannot return, or doesn't return to original length. because you exceed the limit of your elastic limit. Doesn't return to original length. And a few other information that you can get from the graph is obviously the permanent extension. Here to here is your E, your permanent extension. Okay, and this area, this blue, okay, let me show you red. This red color area, this is the energy loss as heat. So that's a permanent extension, okay? And this area under the graph here, this is the energy loss as heat. Okay? So that's how you can interpret the graph. Area under graph is always energy. And if you exceed the elastic limit, that's the energy loss as heat. Sometimes they will give you some fx graph that looks like this. Like that. Then like that. Teacher, what like that one? This is polymer. Okay, no follow Hooke's law. But let's say I switch out the area, okay? So the area under this curve, this is when you stretch. Okay, you apply force. Let me try to follow color. This is F applied. So you're stretching something, the extension increase. This is force removed. So if I look for the area under the large, the top curve, this area, the yellow color area, I'll call this A1. A1 is potential energy stored. Okay, potential energy stored when you stretch, during stretching, or during F applied. Okay, and then this area here, this area down here, is the energy that you return, that you get back. This A2. This is potential energy return when F removed. Teacher, this one no permanent extension. No. Sometimes the graph, you stretch a rubber band. It's like me stretching my hair tie. Stretch, let go back to the original shape. Okay? So returns when F removed. Alright. Then you may be thinking, then teacher, this area means what? This area, A1 minus A2. Sorry, A1, yeah, A1 minus A2. So A1 minus A2 is equal to the energy loss as heat. You cannot get back already, the energy. So if you try to stretch the rubber band a few times, you can feel the rubber band become hot. So the energy loss as heat during the stretching and relaxing process. Okay, so this is how you interpret energy or area under the graph when you look at Fx. Okay, so Fx is easy to tell. Hopefully you already know that the area under the graph will always represent energy. And from here, we can actually know that if we stretch beyond the elastic limit, the area under the graph will tell us how much energy is lost in that process. But what about the stress-strain graph? So what you see here beside me are the stress-strain graph of different material. And you will see that glass is fairly brittle. It doesn't deform plastically a lot. It just breaks. Okay, whereas copper and steel, because they are metal, they will reach a point where you can see the stretching. Okay, so for this one, if you want to know what is the area under the graph, okay, so area under the stress-strain graph is equal to half stress times strain if the Hooke's law is still obeyed. So this is if the limit of proportionality not exceeded. So if I think about this, stress is actually F per unit area, and strain is extension per unit original length. Let me make this L. Okay. And then you see this half Fx is elastic potential energy before Hooke's law, okay, while you're still obeying the limit of proportionality. So this half Fx, I can write this one as strain or elastic potential energy What is AL? Area of the wire times length of the wire is volume. Okay, so this is not very popular, but sometimes they can ask you to prove that the area under the stress strain graph is equal to strain energy or elastic potential energy per unit volume. Okay, there was this isolated past year question where they asked you to prove in paper 2, but it's just as simple as isolating out half fx. Okay, and this will give us volume. All right, so all the interpretation previously still holds, right? So here, if let's say this is fx graph, the area under the graph still holds, the interpretation is still the same. The only difference is all this energy become energy per unit volume. Okay, and the whole return to original length and lost energy as heat is all the same per unit volume. And for the x-axis, it will be per unit length. Okay, let me label the final one. This is permanent extension. Okay, so you really should try out some questions, okay, and watch the example videos. We are going to look at how we will apply these ideas. So the whole bird's eye view is there's this 3 things. One is called stress, and stress is force per unit area. One is called strain, and strain is extension per unit original length. We divide them, you can get Young modulus. So based on whatever graph that you are given, if you want to look for Young modulus, you can use the equation, or based on the graph, you can use the gradient. We can also apply Hooke's law here. And also the idea of area under the graph, depending on what graph you get, is either strain energy or strain energy per unit volume. I think I'll just add this here for comparison. Okay, so area for Fx is a strain energy or elastic potential energy. And area for, if they flip the axis, you find the other area, the one with this one. If they flip the axis, this is strain energy per unit volume. All right, time for you to learn by trying questions. I'll see you in the next video. Bye. Don't stress yourself out too much. Must stress a bit and then return to original length. Sanity is important. Take care now.